So good morning, ladies and gentlemen. I hope you had a nice break and a good entry to the year 2021. We are now back with a training schedule where we left it in December. I am Paul Arranz. You already know me. I'm in charge of the solar photovoltaic sessions. So happy to be here with you again. In today's session, we are going to look at the specific case of the mini-grids, off-grid mini-grids.
Hello, Paul. Don't forget to put this presentation mode.
Yes, I have. Don't you see the presentation mode?
Yeah, it seems to be small.
Hold on. Okay, just a second. Can you see now?
Yeah, we can see it. I was expecting to have my screen, but okay, you can proceed. If all others, they see it at full screen, it's no problem.
You can see it full screen, or you can see the presenter screen, the moderator. Okay, let me try something. Okay, is it better now?
Now is better. Yes.
Okay. All right. Then okay, so let's continue. Today we will be looking at the case of the mini grids, as I was saying. This is a case that it is familiar for you in Mozambique. I mean, there's some different projects already being realized and many more in the portfolio that are at the moment being identified, analyzed, and specified to be built in the coming months or years. Mostly being developed by FUNAI, as far as I know, and also with the collaboration with some private sector companies or other entities. Okay. So let's move on. We will have next week trying to organize a talk from a colleague in FUNAI, okay, that will also share the experience of an off-grid mini-grid, or probably perhaps two mini-grids, okay? So that will be very nice, very interesting. We can also get the direct experience from our colleagues in Mozambique. Okay, just a bit of a reminder. Last year in December, we were discussing about the steps that were necessary for a feasibility study for photovoltaic energy project. And if you remember, we were talking about a first stage of strategic planning, where the different components of sustainability should be observed. Then the site assessment, including, of course, the levels of solar resource that are available on site. The demand assessment, very important for the off-grid projects. The concept of our ¿Sí? Oh, okay, I think that was okay. Just a conversation. Then defining what the outputs and the inputs of our system would be. Finally, the decision about the selection of equipment and components. We also mentioned that there is another step in terms of operation and maintenance requirements and human resources. This we will see it in a later stage, okay, in session PV09, 2 weeks from now, where we will discuss about maintenance specifically, okay. So today we are going to see all these stages from 0 to 6 for the specific case of off-grid mini-grids. If you remember, in the previous session we discussed about the large farms, the large plants, PV farms or PV parks. So we are going to do something similar today for the case of the off-grid mini-grids. Some examples. Just to recap, we mentioned that the space of mini-grids is quite large. Actually, it's quite big. We have different types of mini-grids. Basically, we distinguish those mini-grids that are off-grid or autonomous, whether they go for a high level of service or a low level of service. And then we also discussed about the interconnected, grid-connected mini-grids. Today, we're going to talk about the first ones, about the off-grid. We already saw the case of interconnected mini-grids in some previous sessions. So today, we are focusing on off-grid mini-grids, which is the top part. Just a quick reminder for the strategic planning, we have a vision of integration where we want to have different components. We want to observe the social component, the institutional component, and also the technical, technological component, and the financial and economic. We insisted that when we design solar photovoltaic systems, the goal that we have is to provide an electricity service. Okay, this is very important, really, really important, and especially for the case of off-grid mini-grids or solar home systems. There will be an electricity service, and for that service to be sustainable in terms of technology, technical planning, we really need to observe the reliability of the systems. So this is our main goal when we analyze the technical or technological component. Okay. We also mentioned that very easily in a mini-grid project, for example, in other projects as well, yeah? But specifically for mini-grids, we can be trapped in a vicious cycle, in a cycle where everything goes bad very quickly, okay? If our technical component, our technology, our components, our systems, our PV panels, inverters, batteries are not performing properly, that will create a spiral of customer unsatisfaction, which will lead to non-payment eventually of tariffs. Then this will result in the stop of the operations, of the functioning. There will be a breaking of the service. On the contrary, if all the elements of our project are properly assembled with a good financial structure, with a good contractor performance and equipment performance, that will lead to customer satisfaction, and that will become a virtuous circle. And the electricity service will be running and everybody will be happy. So reliability is one of the two main legs, yeah, by which a sustainable project will be working on. And on the contrary, if our technology is our technical solution is not reliable, we will be, of course, in trouble. Before the Christmas break, we also, if you remember, we also defined, yes, what would be the generic steps for the sizing of solar systems. We talked about the determination of energy demand, If you remember, this is very important. Today we will be insisting on the energy demand. And at the end of the session, you will have a little exercise, a little challenge, okay? So determination of the energy, remember, on a daily basis. This is our main parameter of analysis, what happens on a typical day. And not only what the energy demand will be to begin with, okay, the starting demand, but what could be the evolution in time, okay? Typically, for off-grid projects, we would expect some growth. We would expect the demand to grow after some time. Then the calculation of the solar radiation, okay, and what happens throughout the year. There will be differences from one month to another month. And now, for you is probably the time of the year where there's higher levels of solar radiation in January, December, January, as compared to June, July, where you have lower levels of sun. Okay, from that then we need to worry about the size of the photovoltaic generation, photovoltaic field, in watt peaks or kilowatt peaks, obviously. Then we discussed about the different solutions for the mounting system, for the support structure. Whether we put, for the large plants, remember we were discussing about the tracking systems. This is not the case for mini-grids. Normally mini-grids are smaller in power capacity, and it doesn't really call for solar tracking solutions. For the case of off-grid, where we are now, or for some self-consumption, if it is rooftop, then we need to calculate the battery storage needs, okay? We did some exercises, and we will do, again today, we will revisit the calculation of battery capacity. And finally, the calculation of the power conditioning equipment, the inverters, etc. What is the power capacity of the mini-grid that we want to install? Then there are some aspects that we discussed about the wiring, calculation of the specific layouts, but that is more about every project specific, and that is not really intrinsic of photovoltaics. That has to do with normal electrician work for an electrical solution. So today we will not cover this section. We'll focus only solar mini-grid specific aspects. Okay, this we can revisit towards the end of our program, because this has to do with just standard electrician practice. Okay, so let's move ahead to revisit one of the critical aspects for mini-grid design, which is the load and the demand calculations. I'll be using different examples from our colleagues, some examples of mine, and from our colleagues from Azimuth 360 that you have met in some previous sessions in this course about mini-grids. So if you remember the demand, please be aware, very critical for the off-grid systems and the mini-grid. If we oversize, we will get to inefficient performances, expensive systems that are probably going to be a bit of a waste of money. If we undersize the demand, then there will be obviously low quality of the service, shortage of supply, the customers will not be satisfied, etc. So it's really challenging. We cannot be oversizing nor undersizing. We need to be quite smart with this. Okay, basically, I want to make it clear as well that whenever we approach the demand analysis, always remember that energy efficiency has to be at the basis of what we are doing. If there are some consumptions that can be avoided, that can be optimized, that can be deferred, that can be moved. Of course, this will require training, yes, with the customers, with the communities, etc. That will always create a benefit for the project. And right at this stage, when we are analyzing the demand, is the best time to start or to consider energy efficiency. Sometimes, when the mini grid is already designed and built, it is too late to go back for some of these aspects. Okay, so basically, the first step is to try to understand demand and try to find ways to reduce this demand without, of course, affecting the quality of the activities that the community is trying to develop. Okay, there are a number of tips here. Mainly, the main one probably is to try to adapt the consumption pattern to the solar production pattern. What do I mean? We are going to be producing electricity with the solar system when there is the sun during the daytime. So whenever we can adapt the consumption during daytime, that will create efficiency and it will minimize the need for a battery. Okay. We also discussed about the different levels of energy consumption. If you remember the tiers, different levels of access from very low levels, very low loads, lights, phone chargers, etc., to much higher levels of consumption, air conditioning, different electric appliances, etc. Okay, from lighting, communications, then the productive uses, okay, of electricity, which normally are motor-based applications or even heat generation appliances. We also mentioned about the methodologies to collect energy demand data. We have questionnaires, we have surveys that we can run with the potential customers or beneficiaries. So in this example, we are going to consider around 5 or 6 types of connections or consumers. This is always interesting to do, this kind of analysis, because it is realistic. There will be different types, okay, of families, different types of shops, okay, different type of businesses that will be consuming different types of, will be having different types of demand, from lighting, little electrical appliances, refrigerators, climatization, or warehousing for storage, logistics, etc. Public lighting, etc. Let's start putting some numbers. In a mini grid, we have a situation where an off-grid mini grid, we have a situation where there will be a limited amount of electricity to be shared between the different customers or the different users. Okay, so this sharing has to be done in a proper way to avoid conflicts or tensions between the different customers. This is why it is normally used some smart meters that can have a limitation function. So if you are a type 1 user or customer, your meter will be equipped with a limitation, okay, functionality, so that you always stay at your level of consumption. This can be adjusted. This is just an example, but for instance, type 1, very low consumption, in this example, was defined with a limited consumption of 275 watt-hour per day, limiting at the maximum energy consumption, and the maximum power consumption 500 watts, okay, anytime. That is equivalent this energy consumption is equivalent to roughly 8 kilowatt hour per month. This is very little. So any household that would be subscribed under type 1 tariff or level of consumption will be limited to these levels of consumption and cannot go beyond. So a similar kind of limitation will be done for each type of customer. And this will be programmed, this will be equipped in their specific meter. Okay. So it is important that this demand analysis it is compatible with the kind of meters that are going to be used in the mini grid. This is an interesting aspect for the guidelines, for the specifications of the mini grids. I mentioned to you the previous talk, how are these different types of customers defined by listing the different appliances they can have, number of appliances, how many hours will be each appliance used in a day, and that gives us a typical energy demand reference per day, and we multiply by 30, we have a demand per month for each type of customer. Okay, remember that we can do surveys, but that takes a long time. That is the best. If we don't have time to do surveys, we can also look at the what are the consumption patterns, the histogram of similar villages, similar communities, where we have the different customers, for instance, and what is the level of consumption electricity for each customer in a year. And from this, we can adapt a pattern. In this example, for instance, 11% of the people in the village was consuming between 0 and 20 kilowatt hour per month. 1/3 of all the community was in the next segment, from 20 to 50 kilowatt hour per month. For the next segment, 50 to 100, we find 25% of the community households. The next one, 25%. And we have a small fraction of the community households that would be consuming above 200 kilowatt hour per month. So we do a little bit of a projection, how the consumption is distributed, because not all the customers will be consuming the same. Okay, and in the end, if you remember, try to approach what the load profiles will be when these customers, this type of customers will be consuming electricity. We need these profiles so that we can anticipate the kind of solar photovoltaic solution we will need for the mini grid. We can see, for instance, in this example, a peak of consumption in the evening, mostly due to the blue part, which is the residential. This means consumption at night. We don't have solar generation here, so we need either batteries or some kind of support to the solar system, like a generator set, wind, etc. So we need to approach these profiles to understand the kind of solution we will need for our mini grid. Another aspect that we need to consider, if you remember, is the use of the batteries. The excess generation during the day is stored in the battery for later consumption. In this example, from a real community in West Africa, we can see this is the consumption. This is a community with a lot of productive activities. You see the peak is mostly during the middle of the day, and this is the solar generation curve. So this is when the PV panels are generating. So you can see for this day, the electricity that was consumed and the electricity that was generated by the PV panels was more or less the same. So if we only look at this consumption 25 kilowatt hour. Generation from the PV, from the solar system, 25 kilowatt hour. Perfect. Okay, yes, it is perfect on a daily basis, but if we look carefully, we see that, in fact, there's some time of the day when it is night that the solar system is not generating. So this is when we need to be using the battery. And this battery has to be charged during the daytime. Okay? So the batteries are needed, and in this kind of graphs, we can see what is the matching that will be needed between the solar, the PV panels, consumption, and the batteries. Okay. It is important always in an off-grid system to be looking at the nocturnal fraction of the consumption, meaning how much of the energy that will be used will happen during nighttime. Okay. This is very important, obviously, because this is what we need to size the batteries. In this example, we have a low factor of battery usage. Again, this would be the case of a village with a lot of customers, with a lot of businesses, where most of the consumption, the blue area, will happen during the day. This is when the solar panels are generating electricity the most. So this is a high level of matching. This is a low level, high level of solar matching, low level of night consumption, and small batteries are required here. Perhaps not even batteries are needed here. On the contrary, in a situation like this, we have a lot of consumption during the night, and a lot of the solar generation is not used instantaneously. So it can be stored and used when necessary. This is a situation with a high factor of battery usage, so larger battery bank will be needed here. In the end, when we approach our different consumption levels, apart from the number of appliances and the time of usage for each appliance, it is very important also to look at how much of this use will happen during nighttime. Okay, whether it is, for instance, the lighting, 100% happens when there's no sun. Okay, so one by one, the different appliances that will be needed can be assessed with respect of the battery fraction they will imply, or the nocturnal use. For domestic applications, typically 70 to 80% night fraction is what we find, okay, because there's a lot of lighting consumption activity in the houses. Households is normally in the evening or at night, okay? So high levels of battery fraction are normally expected in mini grids where there's a lot of residential consumption. In any case, not less than 50%. That, of course, depends on each community. Again, if you remember the presentation from engineer Pablo from Studer, he was telling us about the difference between mini grid with only residential users, with again, peak in the evening for the consumption, or a mini grid where there is, different productive uses and businesses where the curve, the load curve, doesn't have these huge peaks in the evening, but higher levels of consumption for the whole day. We also mentioned that the demand has a lot of influence in the design, okay, of our components. The load profile, the types of loads, how this demand is going to be evolving. And finally, a point that I don't want you to forget, that for all mini grids, it is always interesting to consider the possibility of the arrival of the grid. What happens if after 5 years, 10 years, 20 years, the EDM grid can be extended to that area? What are we going to do? So the tip is to always consider inverters, protections, meters that can be compatible with the grid. It might be a little bit more expensive when you build a mini grid, not too much, but a little bit more expensive. But it is a good design decision, because this mini grid today is off grid, but tomorrow can be grid connected. Okay, and all the investment is not wasted. Another aspect I want you to be aware of, the growth. As I mentioned, typically we expect that the electricity consumption will grow. We measure that by means of a growth factor, un factor de crecimiento, which tries to approach what is the rate of the evolution of the future electricity demand until the end of the useful life of the project. Okay. In here, you can also consider different steps. For the initial years of a mini grid, you can expect a higher degree of growth, because in the beginning people don't consume much electricity. Then after 2 years there is a high increase, and then it could stabilize. Then the increase could be a bit more moderated or even controlled. In any case, each community, each village will have its own dynamics, okay, its own socioeconomic effects, possibilities. So it is not advisable, or it is impossible to say you always have to consider a growth factor of this much or that much. This is an aspect of investigation, case by case. What we can see are some references. If we have communities with low energy demand and their demand is basically residential, domestic, you can expect a low level of increase of the demand. Low level means from 15 to 25% of increase, especially in the first 5 years of operation of the mini grid. If you have, on the contrary, communities that can be connected to the national grid very soon, 2 years, 5 years, less than 10 years, the design demand will be more or less constant. Okay, the growth factor could be very little. And finally, when we have a communities, village with great economic potential, but they are very far from the national grid. I don't know, they could be like some settlements, there could be some ecotourism activities, mining activity, forestry activity. Whenever there's a great economic potential, then the increase could be very high, very rapid. It could even double in a matter of 2 or 3 years. So this is very important, the growth factor, and this has to be properly investigated for each project. So every time you approach the design of a mini grid, this is something you need to have in mind. What is the growth factor here? What is the evolution of the demand? Has anybody studied that? No, not yet. Then the project, in my opinion, has to stop and investigate this factor before continuing. Because we can get surprises after a few years of operation of the mini grid. Okay, well, we can discuss different examples, different references, yeah, but typically what we will see would be a growth, yes, of the demand, especially in the first 5 years of operation of the project, and then there will be, that's like a learning period, and then you see the growth could still be there, but a bit more, you know, moderated, a smaller rate of growth. Okay. Okay, another aspect in mini grids is what we call the use factor. The use factor is easy to understand. When we have a limitation of the energy that each user, each customer can use in a mini grid, there will be moments of the day, there will be days in the week that not everybody will be using all the electricity that is assigned for his or her tariff, okay? Imagine that you live in a village and you travel for 2 days, 3 days, because you have to go to the market, because you are visiting your families, because you have a funeral, whatever. So there will be some time where even you have some electricity that you have contracted, you are not using it. You are not using it. So this is a factor below 1 that tells us how much of the contracted electricity is not going to be effectively used, okay? And we use these factors to reduce a little bit the sizing of the mini grid. This is especially important for mini grids that are a bit large. Of course, when you talk about mini grids with 50 families, 20 families, this is not much. You see, for 20 connections, the use factor is almost 1. But when we go above, when we consider larger mini grids, we can introduce reductions in the use factor. We can consider use factors of 80%, 70%, etc. Okay, so that is a factor we can use to reduce the sizing. Another aspect of the demand and the mini grids, the seasonality, is the electricity consumption in the village always the same throughout the year, or do we have some patterns? Is there some time of the year where there is a harvest or post-harvest, I don't know, that the electricity demand is higher and then will be lower? This is important for the sizing, because we need to decide which is going to be the demand, the designed demand level that we will use for the sizing of the PV system. It is different to choose the PV panels capacity to provide a power generation of 70 kilowatt hour per day or 80. This is 15% more or 15% less. 15% more of investment, of cost, or less. Okay, so it is important. And if we choose to size the PV generation capacity here, then what do we do with this deficit? We will need probably to have a genset and run this genset only for the additional demand need that will happen in a period of 2 or 3 years. Okay, that could be a solution. For this kind of analysis, this is why we consider the aspects of selectivity or flexibility in the generation. Which kind of consumptions are we going to consider as priority? Which ones are going to be secondary? Can we consider a strategy to assign the primary consumption with priority from the solar system and the secondary consumption, not so much priority from genset, for instance? This is an example, schematics from Studer, again, from Switzerland, where they can have, you see, different generations, solar generation, diesel genset, or hydro generation, for instance. A mini grid that I worked with, and the company TTA, you can see the solar system, but there's also generation with wind. Okay, so all these different possibilities are of interest for the design of the mini grid generation. Also remember the case of the diesel generator example that was explained to us from Studer. We all try to reduce, we try to bury, to get rid of the diesel. But sometimes when we have a lot of generation, a lot of consumption, when there is no sun, a situation like this, you see the peak. The orange part is where we need the battery to be feeding our demand, supplying our demand. If we consider diesel genset, we can really reduce the size of the battery bank to half and really optimize the performance of the system. A situation like this here, where we have a lot of consumption in the evening, will be most optimally solved by introducing a diesel genset together with the batteries and the solar system. Okay, so the diesel genset is always useful. It is useful to build a mini grid, and it's useful to have it as a backup or as a possibility to adapt to changes in the demand without having to worry about the size of the batteries. But what is the problem with the diesel genset? We have a problem of the cost of the diesel, and obviously the problem of the environmental impact of the diesel. So we really want to minimize the use of the genset. Okay, finally, the estimation of the total demand, the aggregated demand. Remember, what we want to do at the end of the demand analysis is to have a clear result in terms of what is the total daily demand aggregated that we expect in a community. In this example, you see we have all the different households, type 1, 2, 3, 5, then the health center, school, the church, we have some home for young people, community building, social room, pumping station, water pumping station, and the public lighting. See the amount of energy that each of these customers will have, how many units of each customer we will expect. You see, for instance, for the houses, we have 8 families for type 1, 47 families type 2, 31 families type 3. Okay, altogether, this will give the total number of connections that you can have in a mini grid. This is going to be in the range of 140, okay, connections for a community. What is the total consumption for each type of customer, and the nighttime consumption? So the second very important result of the demand analysis is what is the battery or the night demand. In this example, we have roughly we have an 82%, okay, of the night of the demand is going to be nocturnal. And we also look at the power consumption. What will be the power consumption for each of the segments of the customer type? Then we consider a use factor for the energy and a simultaneity factor for the power. And for that, we come up with the final design parameters of our mini grid. The total energy design, this is the nocturnal, the night design, and the total power demand that we need to consider in the load curve. Okay, the growth has to be introduced here. You see the growth forecast. So we have the demand today, the growth, okay, factor, we introduce it here, then the use factor, and finally the simultaneity factor. These are the essential parameters that we will use to size the power capacity, sorry, the solar system in the mini grid. Okay, so you can see it all comes down to a very good analysis of the demand. Okay, if we are going to estimate values, because we don't have time to go there, field work and do the surveys, we can do that, but we need to be very sure of the kind of estimations and the references we are using. Okay, I think it's a bit early perhaps to have a break now. I think we can continue a little bit if you want. Or Carlos, what do you think? Should we stop now or we continue a bit more?
Well, it is always good to have some refreshment. Huh?
Refreshing. So, okay.
Yeah. Maybe we should, I don't know, 5 minutes?
5 minutes. All right.
Or the participants want to have 10 minutes. Oh, silent. This means probably 10 minutes as it is scheduled. Huh?
All right. So
let's take 10 minutes break.
Okay, we take a break of 10 minutes. We come back at 10:05. Okay?
Yeah. Yeah.
All right. Thank you. All right. So we're going to continue. Good. Let me share the presentation again. Okay. All right. We're fine, right? You can see the screen properly?
Yes, we can see it. It's okay.
Good. Okay. So let's revisit all these issues in a specific case of a real mini grid. Okay, it is an example that I have worked out again with our colleagues from Azimuth 360. This is we have chosen a case study of a mini grid in Zambia, in an island. Okay, Chishi Island, which is not far from Mozambique, okay, in the north, Tete province. So it's not too far, okay. So it's I think it's an example that will be, it's very, very easy to connect with the needs in Mozambique. Of course, this is a specific case, so some aspects are unique for this village and need to be adapted for any analysis we would like to do in any other place in your projects, for instance. So let's look at this example. The specific location of Chisi Island is okay. These are the coordinates: latitude, longitude, and altitude. It's a little bit high, sea level. The type of system that is considered here is a mini grid, standalone or off grid, PV mini grid, hybridized with a diesel. Okay, we have already seen where are the advantages of hybrid systems like this. The type of customers are mostly domestic. Residential consumption is what we expect. So when we see that, we can already anticipate that profile, load profile with a peak in the evening. When we talk, when we discuss with our colleagues in the field, what kind of customers we will have in this village. Residential mostly, okay. The first thing we have to click is the peak in the evening, okay. Number of connections, in this example, 137. Type of distribution line, 3-phase and aerial, no underground distribution grid here. The type of batteries, lead acid and flooded, OPZS. You remember from our sessions on batteries, the pros and cons of the lead acid batteries with respect to lithium-ion batteries, etc. So for rural electrification applications, if you remember, lead acid at the moment is still the most appropriate, most cases, type of battery technology to consider. And the use of the backup genset. For this example, because of the solar radiation levels here in this part of Zambia are a bit particular, you will see there is some time of the year around January, February, where the radiation levels are quite low due to combination of rains, climatic factors. So the need for backup generation as a bit consistent in the month of January and February, for a maximum of 2 hours a day of genset, okay, for the low radiation, solar radiation periods. So that's a little bit like the starting point, okay? So what do we do? What I mentioned in the presentation before, we need to analyze in detail the kind of consumptions we will have in this community, in this village. So up to 12 different types of consumption. First of all, the households, 4 types of households. 1, 2, 3, 4, from small consumption or economic, medium, a bit of large consumption, and very large consumption. And we need to specify what are the maximum consumptions, energy consumption per day, power consumption at any time. So you can see from 275 watt-hour per day to almost 2000 watt-hour per day. Okay, these are the different levels of consumption. Then we can have businesses. Of course, for the businesses we expect, or it was determined to have higher levels of consumption. Health center with refrigerations. Now these days we are discussing about the vaccine for COVID, etc. Needs to be stored in cold fridges. So health center needs a substantial amount of electricity. For the school, not so much. The church, different community premises, water pumping station, and finally the public lighting. Okay, so 12 different types of consumption. For each type of consumption, okay, what we did in this project was to analyze the type of appliances. Remember, which type of appliance? This is the tariff number 1, low tariff. So basically we have lighting and mobile phone charging. So very small power needed for each customer in this type. You see 275 watt-hour per day, that is equivalent for monthly consumption of 8.5 kilowatt-hour per month. And the battery fraction, most of this type of consumer is nocturnal, all of it, okay? For the second type of household, moderate, that's where we start seeing more lights, okay? 8 lights, the previous one had only 7, TV already, etc. So double the power consumption, double the energy consumption, more or less, and the monthly reference 16-17 kilowatt-hour per month. This is still very little, but is not as little as the previous one. Then the night consumption is a little bit lower, but still quite high, almost 90%. And we do the same exercise. We did the same analysis for all of the 12 consumption tariffs, okay? Obviously, when you do this kind of analysis regularly, you already have your own like little spreadsheets, okay? Excel sheets to run all this analysis. It's very simple, but it needs to be neat and properly organized. So in the end, for each type of household, we have the power demand, the energy demand, okay, and the nocturnal fraction, the battery fraction. This would be the high comfort domestic type of customers with the fan, with the refrigerators, etc. We call it high consumption, but if you can compare this to what you are consuming in Maputo, probably this is still low, 59, 60 kilowatt-hour per month. That is still low for Maputo standards, but in a rural community, these would be the very high consuming ones. All right. And you see the battery fraction, 80%. For a household, for a residential consumption. For the businesses, it is different depending on the type of business, of course. When there is light and when there is this could be like a little cantina, okay, or bar, or restaurant, place you can eat, or eventually a hostel where you can sleep if you are traveling that region. Then the battery fraction is a little bit lower. Nocturnal consumption is 72%. For the health center, same analysis. What kind of appliances are we going to find in a health center? Some medical equipment, some printers, laptops, okay, some refrigerators. Again, in the end, the demand of a health center, 67 kilowatt hour per month, or 2.2 kilowatt hour per day, and a battery fraction of 74%. For the school, again, most of the consumption would be in the evening. This is a school where they also run lessons for the adults, okay, to learn how to read, or some meetings, okay. So there's a bit of lighting consumption, not too much, 4 hours per day, not many lights, but okay, there's still a considerable night consumption in the school. For the church, a little bit of consumption as well, okay, basically with the fan and a little bit of light and a mobile phone charger. The different halls, community halls, same analysis, okay. This social hall has a mill, okay, for a little bit of agro processing, and this is considered to be used 40% during daytime and 60% during nighttime. Most of our considerations are normally a bit conservative. We try to be on the worst side of things. This means a lot of usage of the battery. We try to be conservative, but of course you cannot invent these numbers here. If you put here 60 or 30, if you put the number of meals, you cannot really invent this number out of the blue. Maputo, you need to discuss with the village. When you do the needs assessment, you have to discuss with them what are going to be these parameters for the community. The pumping station and the public lighting, okay? So finally, we come up with a distribution like this, 137 connections. Most of the connections are in these 3 types of customers. So if you are, imagine you are ADM or you are a private operator of mini grids, you would have 137 subscriptions, 137 clients in this mini grid. But most of your clients, out of 137, you will have that 110 are going to be residential from type 2, 3, and 4. So you have 137 customers, but most of them are in these 3 types here. Okay. The growth factor for this community, we have considered a growth factor flat of 15%. So every year we have a 15% increase, okay, in the consumption. For the use factor, because we have a number of connections above 100, we recommend at least a use factor of 80%. So this is what we take. If we had a smaller number of connections, we would be taking 90%, 95% use factor. In this case, we have 137 connections. We can take 80% of use factor. So we will need this factor when we scale down, okay, the aggregated demand of the community. In this example, in Zambia, Shishi Island, no seasonality in the consumption was found. After discussing with the community, no seasonality, okay? So stable consumption across the whole year was reported. So the aggregate demand, as I told you, That's an important result. In the end, we sum up all the different consumptions for all the types of customers we expect, 137. You see the total consumption from each type of customer, okay? In the end, we have a gross consumption expected in year one, okay, of roughly 6,000 kilowatt hour per month, with a night fraction of that of almost 4,900 kilowatt hour per month, and a total gross aggregated power of 102 kilowatts. That is what our survey and estimation with our tables gave us. Now we introduce the growth factor, okay? So 1% per year in a period of 15 years. So that's an aggregated of 15%, okay? That's what we introduce here to increase the expected demand after 15 years, okay? So you can see there's an increase, almost 7,000 kilowatt hour per month, 5,600 kilowatt hour per month nighttime consumption, and the total power with a growth factor 117 kilowatt. So this is what we expect to have as a gross demand after 15 years because of the growth. Then we apply our use factors and our simultaneity factors so that we can reduce, we can minimize the total design consumption, okay? The design, the demand we use for the design of the mini grid. And these are the final values that we will use, okay? Which is 4,124 kilowatt hour per month, which is equivalent to 136 kilowatt hour per day. And the nocturnal fraction, the nighttime, is 3,362 kilowatt hour per month, which is equivalent on average to 111 kilowatt hour per day. Okay, our net power demand because of the simultaneity factor comes down to 41 kilowatt power demand. Okay, that's at the peak. So some interesting tips or references we take here. We have 136 kilowatt hour per day for 137 connections. So this is giving us a reference, that it can be useful for you in the exercise I'm going to propose to you at the end of the session. So pay attention here, okay? This is a tip I'm giving. 136 kilowatt per day for 137 connections. So on average, we know that each connection has a different consumption. Yeah, of course, we need to, this is important when you do the contract for each type of customer, the type of demand that the customer has selected and will contract. But when we do the sizing, we can get from this example a reference of roughly 1 kilowatt hour for each connection per day. We have 137 connections and 136 kilowatt hour per day of demand. And we can see that more or less 81.5% of the demand. We can take a reference, gross reference. It can be of 80% of the demand nocturnal, okay? Now, we go to the sizing of the mini-grid. The demand is mainly residential, so there's no seasonality. So basically, we are going to consider the month with the lowest solar radiation, okay, as a worst scenario, as a least convenient scenario to take for the design of the sizing of the PV field. So we take a look at the solar radiation remember when we discussed this in class, you have solar atlas maps, you have websites with satellite data, etc. In this case, for the project, we could use the PVGs. It is a website that we described, yeah, from the European Union, the European Commission GIS system, where you can also find data for some European and African locations. So we put here the location of our island here in the tool. You have the website here, and we obtain the levels of irradiation at the optimum angle or different angles, and then different tilt inclination angles, and then we can choose what is the most convenient for our project. But important to go to the specific location. We have the latitude, the longitude, etc. of the site. In here, we obtain the data month by month, and we can see also for different inclinations, different tilt angles. Okay, remember this is radiation, solar radiation figures. We also call this sun peak hours, if you remember. So this is in units of kilowatt hour per square meter and per day for each day. Okay, we look at different tilts, different inclinations of solar panels, 5 degrees, 10 degrees, 15 degrees. And we see that for this specific location, or very, very close location, station in Zambia, for the PV panels looking at the equator, so that's the orientation 0, or azimuth 0, the higher radiation we get is with a tilt of 5%, okay? If we compare 5, 10, and 15 for the worst month, that is the month with the lowest solar radiation, which in this particular location happens to be in the month of January, okay? The average radiation is 6.38, but the minimum, the lowest, is 534 sun peak hours, which correspond to the month of January. Now, this will be different case by case. Okay, it will be similar for any mini grid in the same area, of course, in the same geographic area. But in a big country like Mozambique, you have to pay attention to the levels of radiation you find, because it's completely different in the north or in the south of Mozambique. So you need to run this analysis and make sure you are taking the good reference for your project. In this project, off-grid, mini-grid, we take the worst situation, which is the month of January with the lowest radiation levels. Sometimes you can take the average radiation levels if they are not too different, okay? So for this example, for this project, we ended up choosing the tilt with the minimum monthly radiation. That the minimum monthly radiation is January, and for this month, the inclination that gives us the best performance is 5% degrees, okay? So a position of the panels that is quite flat, almost horizontal. For this situation, we can consider a radiation level of 4.34 kilowatt hour square meter per day. So that is 434 sun peak hours. Sun peak hours, okay? We can even be a little bit more conservative and reduce that if we like. This is engineering practice. Our little friend, the performance ratio, if you remember, the general efficiency of the system. It is a combination of how the system is working and how the consumption is working. So all in all, we have an overall efficiency. Let's revisit these concepts. For the generation, for the PV system efficiency, we have efficiencies of the PV modules, qualities, mismatching losses, efficiency of the controllers, of the inverters, of the batteries. We can have wiring losses in the different cables, etc. All in all, this efficiency can be considered in the range of 75 to 80%. You can take a middle point, 77.5. For the consumption efficiency, battery performance, self-discharging, the battery inverter efficiency, the wiring and the AC side, losses, etc. Again, we can have another efficiency around 77.5. So all in all, we get a combination of the overall performance ratio for an off-grid system with batteries around 60%. If you remember, we have already seen that, yes, for the performance ratio. And what were we saying? We said for the off-grid systems, consider between 55–70%. Okay, so in this example, we take 60% of global performance ratio. Okay, next step, auxiliary source. We said that in this situation, there is in this island there is a couple of months, 3 months with low levels of radiation. If you remember here, yeah, you can see the month of January, the month of February, and December are low, but the rest of the year, the solar radiation is much higher. So we have a local climatic situation here with the rains that really reduces our radiation levels, but only for 3 months, January, February, December. Okay, the rest of the year, the solar resource is quite high. This is why for this case, for this location, we consider the use of an auxiliary generation source, diesel generator in this case, okay? Only to cover what would be the gap between the average radiation level 6.3, 6.4, and this reduction found in December, January, February. So this little gap here with 2 hours daily use of the diesel generator is enough, okay? And we can have a diesel generator, small capacity, 10 kilowatts, 15 kilowatts. So we took 10 kilowatts, okay? So for the use of the diesel genset, with the diesel generator, we want to charge our batteries and also be able to supply a little bit of the demand when the PV system is not enough. I insist, December, January, and February. So for these 3 months, we will have an effective net energy demand that will need to be covered with the generator. That will be the addition of the power demand from the community and the battery charging demand, okay? For 2 hours every day. This is why we consider a factor of 2. So we make this calculation. This is roughly 53.5 kilowatt hour per day will be generated with the diesel genset. So how much electricity do we need to generate with the PV panels finally? So we take the total energy demand. If you remember, the total energy demand from our table is 136 kilowatt hour per day, okay? We take the total energy demand, we divide by the performance ratio, which was 60%, total energy demand, okay? The total gross demand, total net demand, and we deduct the energy that will come from the diesel generator. So the result is 172.6, almost 173 kilowatt hour per day. That is what we need to generate with the PV panels. Okay, so if you remember our calculations, we need to generate 172.6 kilowatt hour per day. We have a level of sun peak hours in the worst condition, which is January, of 534. 534 is the sun peak hour. Remember that we are considering. So we get a sizing of the PV system in the range of 32.3 kilowatt peak for this mini grid. Okay. If we look at PV modules of 400 watt peak each, we need roughly 81 modules. So the first conclusion of the case study, the PV array rated capacity, nominal power, that is needed for this mini grid, 137 connections, Chifi Island in Zambia, is 32.3 kilowatt peak. Okay. If we use 400 watt peak modules, we need 81 PV modules. So that's conclusion number one. When we do the sizing of mini grids, this is the exercise we have to do. Our colleagues from FUNAI, this is what they do, or what they are trying to do for the mini grids. Okay. Now the battery. Remember, the battery, we have been looking at what fraction of the total consumption will be nocturnal. In this example, in this case study, we have an overall consumption of 132 kilowatt hour per day, but the night fraction is 110.6 kilowatt hour per day, roughly 111 kilowatt hour per day. Okay, the type of battery that we are considering for this project, we have considered, is the lead acid open type of batteries with liquid electrolyte. Remember, those are the batteries with the highest performance in the family of the lead acid ones. They have some requirements of maintenance, which is to top up, with distilled water whenever the level of the liquid electrolyte comes down a little bit after some cycles of operation. The depth of discharge of this type of batteries recommended, remember, on a daily cycle is 50%. Remember the presentations we have seen, the battery technologies for lead acid. And given that the customers we have in this mini grid are mainly residential type, also the street lighting, we will have a very intense use cycling of the batteries. So we can consider that batteries will be completing a cycle of charge and discharge every 10 hours. So we use the formulas, if you remember, from the battery sessions I gave you. We have the total energy that needs to be stored in the batteries divided by the that is the efficiency in the consumption and the depth of discharge. We end up having a total battery sizing need of 285.4 kilowatt hour capacity. That is a capacity 10 hours period. Also remember what we said in the battery technology session. The capacity of batteries, it's depending on the period of discharging we are going to use for this battery. Normally, when we approach the quotation of batteries, we use the capacity 100 or capacity 20. This is something that has to be indicated in the specifications of the batteries. So if you want to use the specification on a C10, 10 hours discharge, the result is 285 kilowatt hour of capacity. If we are going to use the capacity over 100 hours of discharge, remember we need to consider some conversion factors that are given from by the same manufacturers of the batteries. In this case, example, we use the Excite batteries. So if we use the capacity 100 reference, we need to consider a factor of 134. So we take our capacity over over 10 hours discharge, and we multiply by the factor 134 to get the capacity for 100 hours discharge. Okay. So remember about batteries, whenever we refer to battery capacity, we always need to make reference to what is the discharge time, because this is one same battery and is rated at 285 kilowatt hour capacity for a 10-hour discharge. Same battery is rated at 382 kilowatt hour for 100-hour discharge. Okay, it is the same battery. Okay, but for the battery sizing, remember that is the battery sizing for 1 day. But normally we want to consider different days of autonomy. Okay, more than just 1 day, because 1 day we could have a storm, we could have some clouds. Okay, so typically we consider more than 1 day of autonomy. In this example, because we have the genset, we only consider 2 days of autonomy. And then the discharge time of 2 days of autonomy increases, okay, to 20 hours of a discharge, complete charge and discharge cycle for our batteries. Because we have the genset and we have a larger daily cycle, longer of 20 hours instead of 10, we can consider a maximum, but this is really a maximum depth of discharge. We can push these batteries down to discharge them up to 80%, but that's really a maximum, okay? 80%. If we consider the 50% that we said before, then the sizing of the battery will be bigger. So bigger batteries and more expensive. So this is really pushing to the limit of reliable, okay, performance of the batteries. So the formula we saw, this is formula I have already explained to you this in the battery session. Number of days of autonomy, and then again we repeat the energy we need from the nocturnal fraction, the efficiency in the consumption, and the depth of discharge maximum 80%. Then we get a sizing in C20, that is the capacity we want from the batteries, the discharge period of 20 hours of almost 357 kilowatt hour. Again, this is the capacity 20. If we want to have the capacity 100, we go to the manufacturer, we see what the conversion factors are to change C20 to C100. We need to multiply by 125. So we do that, and our same battery, 2 days of autonomy, with a capacity of 100 hours of discharge, would be equivalent to 446 kilowatt hour. Okay. So conclusion number 2. The conclusion number 2 is that for our mini grid, 137 connections, worst case analysis in month of January, with the consideration of a genset in the island of Chifi in Zambia, is that we will be needing battery capacity, rated capacity over 100 hours of discharge of 446 kilowatt hour. If we consider a battery bank of battery bases, battery cells of 2 volts each, we would need, we want to put a battery bank of 48 volts nominal in DC. Then we can divide this energy capacity by the voltage, and we will get an amp hour capacity of roughly 4,500 ampere hours. Okay. If we want to do further refinement, we can consider temperature correction. If the temperatures would be a little bit extreme for the purpose of this example, I think this is not necessary, and in this location the climatic conditions are not too extreme. But sometimes if the temperature conditions are going to go above 40 degrees or below -20 degrees at some point, then temperature correction for the battery will be advisable. Okay, so that is the capacity of the batteries we will need for our mini grid. We are doing the same exercise that I did a couple of sessions ago with our PV system in Godoy, if you remember. It's the same routine, but this time we apply it to a mini grid. Finally, the inverter power. If you remember, we have a growth factor of 15% that we have investigated and adopted. And we also mentioned a simultaneity factor. Those of you who are knowledge or practice in the electric engineering field, you know that when there are different loads, this happens in our house, in a community, in a building. Whenever there are different loads, not all the loads will be on at the same time. When you are in one room, hopefully you are not in another room, meaning that you don't need both lights on, hopefully, in your house. Okay, so you will turn one on and turn the other one off. So the larger number of loads you have, the higher probability of not using them all at the same time you will also have. So in a mini grid, with the number of connections, an increasing number of connections, we can have a smaller simultaneity factor. Okay, and when we are above 50 connections for a mini grid, typically we start considering simultaneity factors below 40%. Okay, so we use this simultaneity factor to downsize our gross power demand in the mini grid. Remember, this comes from our table of the demand here. Okay, have 102 together with the growth factor 117. Then we apply the simultaneity factor 35%. We bring it down to 41 kilowatt net power demand for this community. That would be the peak. We expect it to be in the evening. Okay, so yeah, if we consider a simultaneity factor of 38% instead of 35, we get the nominal, the peak power demand around 44.6, 45, let's say, kilowatt. Okay. So the conclusion number 3, and this is the last one for this example, is that the inverter power capacity we have defined to be necessary, yes, in this mini grid will be around 45 kilowatt, okay, of AC power, and the input voltage of this inverter coming from the batteries will be 48 volts on the DC side. Okay. Okay, we are now almost finished with the session today. This is the last 10 minutes we have today. And for that, I want to propose to you a challenge or a small friendly exercise. Okay, I hope you find it friendly, at least. So we have this mini grid in Mozambique, in the province of Tete. I don't know, today, colleagues from FUNAI, you are probably familiar with this case because it's a mini grid that FUNAI has has developed. Yes, so this is a real case in Mozambique, in a community of Fortuna. So I propose to you this little exercise to calculate what kind of sizing would be appropriate for the mini grid in Fortuna. This is just a calculation exercise. So you know the location of Tete province, obviously. Latitude and longitude, okay, this is informative but not so relevant. The most important thing is the irradiation. I'm giving you this factor, so you don't have to worry about that. Remember our good old friend, yes, radiation maps. We are looking at the areas here, Tete province, and we can see from the color code that more or less an average value of the daily irradiation about 5.8 kilowatt hour per square meter. This is the sun peak hours. Okay, you can use this level here. Okay, so we take this level of solar radiation, the type of system in Fortuna community. Let's make it simple, 100%. Okay, solar, so no use of diesel. Let's make it for this exercise 100% solar. The type of customers we have in this community are basically residential and some services. Okay, 66 customers are expected in the Fortuna village in this mini grid, and the type of batteries, yeah, again, flooded lead acid OPZS. Okay, battery type. I'm also giving you what the expected nocturnal demand will be. Well, no big surprise here, 80%. You can consider that. Sorry, I can hear somebody. Is there a question? Okay. Okay, so the challenge. Your bit of homework. You don't have to reply now. Please take a look at these issues, and we will start next week. The next session, next Wednesday, we will start with these questions to you. I will ask you again these questions, and you will tell me which option do you think for you, according to your calculations, which one is more, makes more sense. Question number 1, what would the energy demand be in this community? Okay, you don't have time to go there now to ask, but what demand would you expect? You have this data, 66 customers, 80% nocturnal demand, okay, 100% PV. What demand would you expect in this community? Option A is 140 kilowatt hour per day, option B 67 kilowatt hour per day, or option C 35 kilowatt hour per day. Okay, you don't have to answer now. Let's wait until next week. Okay, we will do a bit of a poll. We'll make it easy for you. Don't worry, you will see with the same Zoom system online. Question number 2 that I will be asking next week. What would be the appropriate PV generation capacity for the Fortuna village? Is it 20 kilowatt peak or 10 kilowatt peak or 40 kilowatt peak? What do you think? You make your calculations, you revisit the notes of today's session. You can redo the same exercise I've done for the community in Zambia. You can do the same exercise for community of Fortuna. And final question, what would be the appropriate battery capacity? I give you 3 options in C100, all of them. So remember what you will have to do. If we consider an autonomy of 4 days, not 2 days, 4 days. Why 4 days? Because we don't want to have to use the diesel genset, okay? So let's assume a very wide autonomy of 4 days to be really comfortable with a battery bank that can give us the possibility even to increase customers if needed, okay? Let's do, it is an exercise. Let's run it like that. What would be the appropriate battery capacity on 100 hours discharge for the community of Fortuna in the province of Tete? Next week, I will start the session by asking you these questions. So I look forward for your answers, okay? And later on, we will have a presentation from Funai about this mini-grid in Fortuna. So you will see what the project has been realized, has been installed in Fortuna. And remember, we are talking about engineering, so there is no one solution perfect always. It's calculations, it is assumptions, it is hypotheses, okay? It is demand analysis with different rates, with different estimations. So it could be that I have a sizing result and somebody, a colleague, has a slightly different one. The important thing in engineering is that we can explain why we are doing what we do, that we have arguments, okay, justification, technical justification for the selections and the decisions we take as engineers. This is what we need to be prepared for. And then we can compare and we can discuss whether this estimation is better, this estimation is too optimistic, or it's too conservative, it's too expensive, or it's too restrictive. Okay, but there is no absolute correct result and wrong result. As engineers, we know this is not how we work. Okay, so thank you very much. This is as much as I wanted to share with you today. In today's session, I think we have about 5 minutes for some questions. If there are any questions, that is, you have received all these notes, or you can download them from our Dropbox platform. And I look forward to seeing you next week. We will start with the questions. These questions, 3 questions I gave you, and then we will see the example of Fortuna in detail with our colleagues from Funai. Dr. Lucas, I don't know if there are any other remarks, or if there are any questions. Now is for everybody, now is the right moment for the questions, please.
May I ask you a question?
Yes.
First of all, are you recommending some kind of software to take easy these calculations? And normally, how the softwares are accurate for this kind of calculations?
Okay, thank you, Senor Frade. To be honest, I don't recommend using software for exercises like this, because software will give you some result very quickly. And the risk is that if you don't know how to calculate these things, you will not know if the result from the software is good or is bad. You see? I recommend using softwares when you generate different alternatives. Okay? For instance, what do I mean by alternative? When you get to a situation like this, then you do your first design for autonomy of 4 days, and you get a sizing, then you can get your price. Then you think, okay, what if I use autonomy of just 1 day, or 2 days, or 3 days, or 5 days? Then I run sensitivity analysis. Then I can use software to do this sensitivity analysis quickly and generate alternative that I can compare. but I can compare to the alternative I have calculated that I know it's my reference. You understand? Same for the demand. In the demand analysis, as you have seen, there are different estimations. What if I put the public lighting, or what if I take it out? What would be the cost? What would be the efficiency? Softwares are good, are useful to run very quick sensitivity analysis. But for that, you need to have your first, let's say, your basis that you have calculated with your knowledge on solar energy. And you know that makes sense. What is the most used? I don't want to say the best because there's always very good solutions. But this software here, Homer, is very popular for the modeling of mini grids. I think I mentioned that in the previous section, okay, in December. I think it was the 3rd of December. This is a software that you will find very popular. Many people are talking about Homer Energy. It is not very expensive. You have to pay to use it. Of course, there's a license, around $500 a year. You can have the basic license. But the problem is that you will start with Homer, and very quickly you will see a lot of data, a lot of things that if you don't know what you are doing, it will give you a result and you will not even know if this result is good or not. You understand me? It's very powerful software, but you need to understand the basics of what you are trying to find out with the software. Yes? I hope I'm getting myself understood. Yeah?
Yes, I understood. And also, I do have another question is related to the growth factor.
Yes.
You mentioned that we are considering one horizon of 15 years. It is not too much, or in this case, it's not possible. We fractionate the growing, say, in 2 or 3 years time, in order we do a parallel grid systems to avoid big mistakes on these evaluations.
Yes, it's 15 years can be a long period. You are right. This is why I told you normally the first 5 years are where you will expect to find, at least according to my experience, the most significant increase in the demand. Especially the first 2 years, but let's say 5, okay? You see in this graph, which is a complete, this graph is not theory. This is the observation of our real projects, mini grids. Yeah. After year number 5, you still have some growth, but you know it's a bit more slow. The biggest change you'll find it in the first 5 years. So I agree with you, Mr. Frade. We can probably narrow down this period of analysis for the growth down to the first 5 years. I agree with you. 5 years is also good, but if you want to be, you know, completely a bit more complete analyst from the life cycle, operational lifetime, yes, period, our PV system, the mini grid, will have to work very well, perfectly well, at least for the first 15 years. So this is why we consider 15 years as the minimum operational lifetime of the battery. You know, the PV panels come with warranties for 25 years. So it's more than 15 years. But for the practical aspect of the business model, of the tariff system, I agree with you. The first 5 years are the most important ones to anticipate what can happen in terms of growth.
And finally, the last question is related to the possibility to evaluate the consumption in the different users. You mentioned that we may evaluate or we may calculate, but also there is some kind of meters that can tell us during the day what is the consumption. It's not easy. We use a genset to together with this kind of meter straight away installed in the consumer in order we identify the pattern of consumption to facilitate all of these, say, theoretical calculation during the day and during the night? Is it not more recommended to use this instead of we make such kind of survey where the possibility of mistakes is quite high?
Okay, you know, the consumption, it is a bit tricky because it is mostly conditioned by the tariff they will pay. You see, if the electricity is cheap, the people in the village probably will tend to consume more electricity. If it is expensive, obviously they will consume as much as they can pay. So the risk of doing what you are proposing, which is it's an option, is that if you just generate electricity for free, then people can be consuming a lot of electricity because it's for free. You understand? The moment you put here your economic analysis and you say, okay, these people want to consume this very high level of electricity, but when you put a price for that, then perhaps this price is too high, then they cannot pay, then they will not consume this much, they will consume less. Okay, so this is why the electricity demand is a very delicate aspect, okay, that you need to approach from different angles. One are the surveys. If you can sit down, discuss with the people, in parallel, you start doing your financial model. Remember, this is an integrated approach. You have the technical part, but you also have the financial part. You start running your business approach to try to calculate what the minimum tariff will be for this mini grid. We will see that in the coming sections about financial evaluation with Professor Bart as well. We will discuss this. Don't worry, we will see more of this. But if you don't put a tariff, it's difficult sometimes to anticipate the realistic demand that you will have in a community. Okay. Another option, if you remember, is to go back to the what are the consumption levels that you find in similar communities. This is something I really recommend. It's this one, right? Yeah. When you have the possibility to look at similar villages, okay, you go to the nearest village where ADM has customers there and there is data, and you can find, hopefully, with EDM, you can find what is the levels of consumption you have in this similar village. And then you can get your anticipated histogram, what you expect in a similar village. Yes, you understand? So then you go a little bit more with a better direction. Similar villages, you expect similar profile, and at least you can start distributing your expected demand by the different segments. Below 20 kilowatt hour per month, 20 to 50, 50 to 100, above 100, this is 100, between 100 to 200, and above the 200. That is another option I use to analyze the similar villages. Of course, every village can be different, so you cannot take these as absolute. So you can try to do, the best option is always try to do all the different methodologies. You use this one, similar village, you also do the surveys, and etc. Then from similar service, similar communities, you can get, quick references. For instance, this one here in Zambia gave us the reference, yeah. of more or less 1 kilowatt hour per connection every day. That is a quick reference. It depends, Mr. Frade, on the level of analysis you want to do. If you want to come up with a first sizing, which can have a bit of an error, but still a well-directed one, with 10%, 15% error, you can do a quick analysis. If you really want to go for very fine analysis, try to minimize the risk of not designing it. It's not really, I wouldn't really say it's a risk of not doing a good design. The risk here is the evolution of the demand. You see, it's unpredictable sometimes. Who knows how the demand in the village will evolve? Even if you ask the people, you're asking them about what they're going to do in the next 5 years. Some people might know, some people will not know, some people will think something, but then they will do something different. This is life, yes? So this is why you need to run different scenarios. Different scenarios, different possibilities. I think I mentioned that as well, the scenarios. This is how I work. This one, you see, this is one same community, okay? One same community in Ghana, West Africa. This is my first scenario, baseline. This is the same community, yeah? This is my baseline. Then scenario one, I consider the growth, only the population growth, 2% per year. And then scenario two, this is population growth, plus I anticipate that eventually there will be more productive uses of electricity, more businesses flourishing in the community. Look at this. I mean, from one scenario to the other, there is double capacity. So yes, the variability is quite important. Baseline, you see, the peak power baseline 15 kilowatt and scenario two is 33 kilowatt. So really the difference between one scenario and the other, yes, is quite remarkable. It's true. But these are possibilities, all of them. This is baseline. They stay as they are. Probably is not very realistic, but it could be. And another scenario that they really boom, many people come to live in this community, then many shops are open. So this probably gives us a range of possibilities between what we could say is a minimum, this one, and probably a maximum, this one. And yes, there's a lot of variability, but we have it, now we have it in a range. We know, for instance, that in this community, it makes no sense to put 50 kilowatt mini grid, 100 kilowatt mini grid. That's too much. It's too much. 100 kilowatt is too much, even for the high-end projection. You understand? So we can frame, we can set the maximum and the minimum with our scenarios. So we know that very probably what's going to happen will be in between. You understand? This is why the modularity, the flexibility in PV systems is important when you do projections like this. This is why in the example from Zambia, we have introduced the genset. That is an additional generation source that can help us to top up quickly in case there is an expected increase in the demand, very high increase. Then if this is really consolidated, then we can do another intervention in the mini grid. We can put more panels, we can put more batteries. Yes, PV systems are modular. You can always, grow them. But to have the possibility to react very quickly, if you are a service operator, if you are ADM or your mini grid company, and you have your contracts with the customers, you need to give them electricity quickly if you want to be professional and fulfill your contracts. Okay.
Okay, thank you very much.
Thank you. Okay, so it's now 11:15. I think it is time really to close now, unless there's a very quick another question or comment.
Well, maybe if we just wait 1 minute to hear from someone.
Otherwise, we will, yeah, remember next week we'll start with the questions that I gave you.
Yeah.
3 questions, so you have a little bit of homework this week from me. Question 1, energy demand. Question 2, PV generation capacity. Question 3, battery capacity for autonomy of 4 days in Fortuna village.
Okay, it seems that there is no more questions.
All right, so thank you very much, and see you then next week.
Thank you very much, Paul. Thank you very much to everyone.